12.8. Curvilinear motion using cylindrical components. Determine the velocity and acceleration components using cylindrical coordinates is the today's objective. Cylindrical coordinate system is useful when particle has motion in curved motion along 3 dimensions. For example, if we consider this person as a particle or going from all the way top of the slide to the bottom, that person actually goes through the spiral motion, and the position, velocity and acceleration of the person changes as he comes down from top to bottom. And to calculate that, we can use cylindrical coordinate system, where we can measure how fast the person is going away or towards the center of the slide. So that is called the radial component of the acceleration, and let's define R for radial component of the acceleration or radial coordinate system, radial axis. Then second, how the angle of the person changes with respect to time as he goes through the spiral motion. We call that motion transverse motion, and define the coordinate axis theta for that. And third component is how fast person moves from top to down along vertical direction. We can define that using the vertical axis or z coordinate system. So for cylindrical coordinate system, the axes are radial, transverse, theta, and z. You can compare this as, if you would like to compare this with Cartesian coordinate system, this is like equivalent to x, y, and z in Cartesian coordinate system. But instead of x, y, now we have r theta, and z has the same meaning as Cartesian coordinate system. And this is the formula to calculate the velocity in cylindrical coordinate system. Now, this is more about actually polar coordinate system. Now, polar is subset of cylindrical coordinate system. In cylindrical coordinate system, we have r, theta, and z because the particle has 3-dimension motion. If particle has motion only along a plane, along the curved path, then we use only r and theta, and that's called polar coordinate system. So remember that the polar is subset of cylindrical coordinate system. In polar coordinate system, the velocity vector can be defined as this equation, where term theta dot is called the angular velocity of the particle. And the speed of particle in a cylindrical coordinate system, the speed of the particle in a cylindrical coordinate system is defined as this equation. Okay, so we will learn that through the presentation. So look at the application example, that a cylindrical coordinate system is used in cases where the particle moves along 3D curve. In the figure shown, the box slide down the helical ramp. How would you find the box's velocity components to check to see if the package will fly off the ramp? So we would like to make sure that the box stays on the track as it spiral come down from the top to bottom, and that's possible only if we know the acceleration of the box, and in order to do that we need to know the velocity of the box as well. And since it's a 3-dimension spiral motion, we use cylindrical coordinate system. Same example, spiral slide. We can calculate the girl's position, velocity, and acceleration using cylindrical coordinate system. Now for cylindrical we use for polar coordinate system we use r and theta. For cylindrical we use r, theta, and z, where z axis is perpendicular to both r and theta. And this is the derivation of the formula. So total velocity in cylindrical or polar coordinate system in polar coordinate system, the velocity can be written as v equal to r dot ur, where ur is the unit vector in radial direction, which is here, and u theta is unit vector in transverse direction, and r dot is the change in velocity in radial direction, and r multiplied by theta dot is change in velocity in angular direction. Remember that r dot is nothing but derivative of r relative to time, and theta dot is derivative of theta relative to time. Oftentimes this is also called angular velocity omega. Similar to that, r double dot is called second derivative of r, which is d square r by dt square, and theta double dot is called the second derivative of theta relative to time. and this is also called angular acceleration alpha. So we can calculate total velocity by calculating the radial and transverse component of the velocity using this formula like r dot and r theta dot. Then write the velocity as a vector and get the magnitude of the vector using this equation, which is square root of r dot square plus r theta dot square. Acceleration calculation involves more parameters. So acceleration has also radial component and transverse component, and their formulas are given here. And total acceleration can be calculated using the vector addition of these components. And if the particle has 3D motion, then we also have z component, which is z dot uz, where z dot is dz by dt, the rate at which z axis or z motion changes for the particle. And acceleration has third term z double dot, which is called d square z by dt square.